So I'm going to take the camera. Alright guys, what we have here is a DC motor, and we're going to explain what these parts are. And it's kind of a flimsy motor, so it might only work once. That's why we're recording it to show that it does work. Here in my hand I have an armature from a professional commercial motor. I want you to notice that it has 5 magnetic surfaces. 1, 2, 3, 4, 5. I want you to notice the amount of wire which is wound very tightly on each of the legs of the armature. Now, the greater the number of turns of wire, the stronger the magnetic field. So as electricity travels through the wire, it creates a magnetic field, and that magnetic field becomes what energizes the armature. I also want you to also notice that the armature is laminated metal. You see the little cuts in within the metal right here? It's not a solid piece of metal. And the reason the metal is laminated is because, unlike a conventional magnet, which when you pull a magnet to another piece of metal, it becomes magnetized. An electrical magnet, once you stop the electricity, the magnetic field stops also. Now, what we found through time, mostly in the 19th century, is that when the metal is solid, even the magnetic field is stopped electrically, the current is stopped, the metal is magnetized if it's a solid piece of metal. But when it's laminated, like you see here, it's multiple pieces of metal, the magnetic field drops when the electricity drops, when the metal is laminated. When the metal is solid, it holds on to the magnetic field even when the current stops a little longer. We want the current to release the magnetic field the moment the electrical field, the current stops passing. We want the magnetic field to stop at that same instant of time. So you notice in the professional armature, you notice the metal is laminated. I also want you to pay attention to this part called the commutator. You notice there are 5 magnetic poles, 1, 2, 3, 4, 5. Also notice there are 5 commutator rings, 1, 2, 3, 4, 5. So each of these poles, you notice there's a piece of very thin layer between this piece of copper and this piece of copper. That's because without that little cut prevents this making electrical contact with that. So as this spins, the brushes are touching the armature without shorting out the armature. Now over here we have a homemade armature. Let's compare the difference. The difference is, first of all, it's number 8 wire versus number 16 wire, which means it's possible to get much fewer turns than with much thinner magnet wire. This is the thinnest wire you can buy that you can hand wind. It's impossible to wind this except to wind it by a machine. This is the thinnest of a thread of a needle. Number 8 wire is the smallest you can wind by hand. Also notice that this is only a 2-pole armature. 1, 2. This is a 5-pole armature. Notice this armature consists of many pieces of metal. This armature consists of only 1 piece of metal. Notice this commutator, it's the same concept, but it only has 2 connections. 1, 2. Now the difference between the commercial armature and the homemade armature is that this piece has a nice round surface, and this is just a piece of metal. It was impossible to make a brass surface of semicircle circumference without having it also touch the other metal and shorting it out. So we have a semicircular circumference of 1 piece of the commutator, but we have just bare metal for the other piece of the commutator. This is called the commutator. When electricity passes on this side of the commutator with these 2 brushes right here, when this brush is positive and this brush is negative, this becomes the North Pole and this becomes the South Pole. When this brush is opposite and this is plus and this is minus, this becomes the South Pole and this becomes the North Pole. Now when the pole reacts against another pole, it repels like any other magnet. So the principle of an electrical motor is the principle of magnetic attraction and repulsion. If you notice, these 2 magnets are north attracting south. They pull each other. But if I do north to north, they repel each other. Now this is called the stator. we're going to put these two permanent magnets on the stator. The idea is that the armature, as it spins, north of the armature will be attracted to the south of the magnet, and the south of the armature will be attracted to the north of this magnet. As the armature spins, now its polarity changes electrically. Now this becomes south and this becomes north. Now it's repelled by this magnet but pulled by this magnet. And so if you notice in the construction of this motor, originally there's a winding in this stator. Originally the goal was to create an electric magnet for the stator, but it was simply not enough turns of wire to create a strong enough magnetic field to spin the armature. So permanent magnets had to be used instead of a electrical magnet for the stator. Now in the commercial motor, the stator is also electrically and magnetically wound, but I didn't have this kind of thin wire by which to wind the stator. So this wire on the stator, it merely holds this stator to this surface so it doesn't come apart. On the bottom of this box, you will see these two connections which were soldered to these two brushes. These two brushes will make contact with the commutator, causing electricity to flow. Now because it's not a commercial motor, it's not a professional motor like in a real application, you have to hand help the brushes achieve contact. It's not going to be in good contact like in a commercial device. If you look at a commercial motor, you notice the brushes are magnetically attracted to each other, and they're also spring-loaded. See that? That helps the brushes make a very good contact with the commutator. You see how that springs back to normal? Whereas over here, we have to help the brushes make contact by helping it along. Here, the spring action helps it along in a commercial motor. So comparing this house motor versus a commercial motor to show some of the differences in construction. The principle is the same, but this is a little bit of a rinky-dink construction, and so you can't expect the professional results of a professional motor. Also in a professional motor, the winding is enclosed in the casing. Stop recording. Okay, so now the armature is inside the housing between the two magnets. Now notice no electricity is applied yet. Notice this is that connection. The reason I'm showing you this is I want to show you how the armature spins without electricity being applied. And for those of you who ever balance a tire know what a balancing means. Because the winding is done by hand and it's not wound equally, notice if I spin it freely without electricity being applied, notice it doesn't spin smoothly. And the reason is, it's not because there's interference, it's because the weight of the wire is not equally distributed in both sides of the winding. So the motor doesn't spin with smooth action because the weight of the wire is not distributed equally on both sides of the winding. So notice if you spin it fast, notice the winding is not, the weight of the winding is not balanced, making this spin, even without electricity applied, a little bit wobbly. You see that? So take it that this is not a commercial motor, and it's not going to work with the same smoothness. And you have to also press the brushes by hand, and you have to play with it a little bit in order to make it work. So please forgive me because it's not going to work right away. You have to play with it in order to make it work. Now I'm using these pliers which are insulated. As you know, an insulator prevents electrical current. And what I'm going to do is I'm going to take one of the brushes, I'm going to touch it to the electrical brush. These are called brushes. This is called the armature, this is called the stator. Okay, so now we're going to position everything more or less in the right position. We're going to take two D batteries. Each one is 1.5 volts, which means it's 3 volts combined. And we're going to show that 3 volts is not enough to spin this motor. Now in order not to touch the brush by hand and it gets hot, I'm going to use these pliers to touch the brush to the commutator without having to hand touch and hold the brush, because I don't want to burn my hand from all the current passing through it. Even though it's low voltage, it's only 3 volts, when you have a lot of current flowing through a relatively low resistance, because this armature has very little resistance. If anybody knows Ohm's law, that means it doesn't have that many ohms. It means that you have passing a lot of current without a lot of resistance, and so it gets hot very quickly. Even though it's very low voltage, the current has no resistance. So now we're going to take the brushes. You notice that it wants to spin. You see how the armature is like wobbly? You see how it's shaking under the force of the magnet? But it doesn't want to spin. Because with this kind of magnetic field strength on the permanent magnet side, now we're going to disconnect 3 volts, and we're going to hook up 6 volts. We'll see what happens. And we'll see if there's enough magnetic strength in the armature relative to this stator. That this is 4 batteries. These are C batteries, which means they have less current, but the voltage is the same. 1.5 volts per battery, 4 batteries, 6 volts. We're going to hook up, now plus and minus in this case is arbitrary. All the plus and minus will do is determine the direction of spinning. So if you hook up the plus wire to the red and the black to the black, it'll spin clockwise. If you reverse the wires, it'll spin counterclockwise. So all the polarity in the DC motor does, it determines the rotation of the spinning. It's actually not a circuit which is sensitive to polarity of the juice applied. It simply spins clockwise or counterclockwise depending on which way the wires are hooked up. So if you notice, I'm hooking up black to black. We're going to make the motor spin clockwise. If I was hooking up red to black versus red to red, then it would spin counterclockwise. So the polarity of the wire determines the rotation of the spin using something called the right-hand rule. Flux, magnetic field, direction. Ouch, it's so sharp. Okay, I'm going to put the armature back onto its pivot point. Notice the brush is not making good contact, so I have to play with the brush to make this motor start. I'm going to hook up the brush by holding it. And you have to play with it to make it spin. The reason it's not spinning is because the motor is not balanced well. There's a lot of friction. So it's not spinning because of electrical reasons, but because of mechanical construction reasons. It was just spinning before. It's just spinning. The problem is this mechanical construction has so much friction and so much unbalance that because of that it's hard to get it going.
Oh.
See? Because the communicator doesn't have the brushes all equal around on both sides. Okay, leave it alone. So, what? I'm enough.
No?
Как не нукай. It's not. You have to make it start by making it resist motion.
It's working! Yay! Project is working!
So the way you make it start is it fell off, the armature fell off. Okay, that's enough.